sequence of real numbers. So a sequence an is said to have a limit L belongs to R if for every epsilon greater than 0, there exists a natural number n depending upon epsilon such that an minus L modulus is lesser than epsilon for all n greater than equal to n, capital N. So what they're saying is, this is if this is your L, you take any neighborhood around L. So this is L plus epsilon, L minus epsilon. So your sequence after some capital N will be inside this. That is an plus 1, an plus 2. The tail will be inside this. You look at this equation. This equation tell you an minus epsilon is between epsilon to minus epsilon. Then an is between L plus epsilon, L minus epsilon. So that means an belongs to interval L minus epsilon to L plus epsilon. For all n greater than equal to capital N. That is, after some time, the sequence will be inside this interval. Okay, that's what convergence means. Example. First one, prove that limit n tends to infinity 1 by n is equal to 0. So using epsilon delta conditions, you have to prove this. So your L, we have to show that it is 0. So 1 by n modulus is lesser than epsilon. Then 1 by n is positive. So this is lesser than epsilon. So n has to be greater than 1 by epsilon. So you choose your capital N to be 1 by epsilon and greatest integer of 1 by epsilon. So this is if and only if. You can go back from here. So that means for all n greater than capital N, an is lesser than epsilon. So definitely the sequence converges to 0. Next question. Prove that limit n tends to infinity 1 by n plus 1 is equal to 0. So how will you do it? So again 1 by n plus 1 modulus assume lesser than epsilon, then this is equivalent to 1 by n plus 1 is lesser than epsilon. Then this is same as 1 by epsilon is lesser than n plus 1. then this is same as n is greater than 1 by epsilon minus 1. So you choose your capital N to be 1 by epsilon minus 1 and greatest integer of this one. So for n greater than n, your an is lesser than 1 epsilon. Example 3. Prove that limits n tends to infinity 1 by n square plus 1 is equal to 0. So try this one.
हो गया
Capital N क्या मिला?
रूट ऑफ 1 माइनस एप्सिलॉन बाय एप्सिलॉन.
हाँ. So let's see. So 1 by n square plus 1 modulus is lesser than epsilon. This is same as n square plus 1 is lesser than epsilon because this is positive. From here, 1 by epsilon is lesser than n square plus 1. From here, instead of मुस्कान कैसे किया ये वाला बताओ?
सर 1 माइनस एप्सिलॉन इसको 1 को इधर ले गई.
हाँ, so minus 1 plus 1 by epsilon is n
greater
square.
than n square. Sir, then n is always greater than 1 minus epsilon by epsilon का रूट. इसका अंदर स्क्वायर मतलब 1/2 कर दिया दोनों साइड.
हाँ, ठीक है. So n is greater than 1 by epsilon minus 1 square root. But you have to choose your 1 by epsilon to be greater than 1. So your
Yes,
epsilon
sir.
has to be lesser than 1. Then only this will be hold. Your epsilon has to be lesser than 1. But if your epsilon is greater than 1, then this will not be possible. So what you have to do is,
Sir, epsilon is a small number. It is always less than 1 ना.
हाँ वो हाँ ट्रू है बट ठीक है मतलब so you can choose your capital N to be square root of 1 by epsilon minus 1. I was thinking of something else also. Look, 1 by n square plus 1 is lesser than 1 by n square. And let's suppose this is lesser than epsilon. From here you will get n to be greater than 1 by root epsilon. So you can choose your capital N to be 1 by root epsilon. And this will be true for every epsilon also.
Sir, in this 1 minus epsilon is very small number and this is approximately equal to 1. It's the same case.
हाँ सेम ही बात है वो. Next question. Fourth one, prove that limit n tends to infinity 2n square plus 1 by n square plus n is equal to 2. So 2n square plus 1 by n square plus n minus 2 modulus. Then this is 2n square plus 1 minus 2n square minus 2n divided by n square plus n modulus. And this is 2n square get cancels. We get 1 minus 2n by n square plus n modulus. Write this as 2n minus 1 by n square plus n. This will be positive because n is greater than 1. So this is lesser than epsilon. If you do it this way, then you have to solve the quadratic equation. Instead of this, you do it, this is lesser than 2n by n square plus n. And this is again lesser than. So your 2n by n square plus n is lesser than 2n by n square, and which is nothing but 2 by n. Now put it lesser than epsilon. So you choose your, so this will give you n is greater than 2 by epsilon. So choose your capital N to be 2 by epsilon, greatest integer function. Okay.
Okay, sir.
Question number 5. Prove that limit n tends to infinity 1 by n raised to the power p is equal to 0 for every p greater than 0.
Sir, n is to be one greatest integer 1 by epsilon to power p.
Yeah. So 1 by n raised to the power p is lesser than epsilon. Then 1 by n is lesser than epsilon raised to the power 1 by p. P is greater than 0. So from here your n is greater than 1 by epsilon raised to the power 1 by p. So your capital N has to be 1 by epsilon raised to the power 1 by p. Seventh, prove that limits n tends to infinity r raised to the power n is equal to 0 if modulus of r is lesser than 1.
That is n is greater than integer epsilon 1 by n.
Let's see. So r raised to the power n is lesser than epsilon, but we have to take the modulus. So this is modulus of r raised to the power n is lesser than epsilon. Then तुमने क्या किया फिर?
सर दोनों साइड 1 by n से मल्टीप्लाई कर दिया.
देखो ठीक है. So modulus of r is lesser than epsilon raised to the power 1 by n. But we need n, na? How will you find n?
Sir, in this, our n is always greater than
N is greater than equal to 1 sequence hai.
yes, sir.
So how will you find n from here? So you do it this way. You take ln both side. Ln is an increasing function. Logarithmic is an increasing function. So ln of modulus of r raised to the power n is lesser than ln of epsilon, because ln is an increasing function. From here you will get n times of ln modulus of r is lesser than ln epsilon. So now we have to be careful about this, because modulus of r is lesser than 1. Then ln of modulus of r is negative, and epsilon is also lesser than 1. So ln epsilon will also be negative, lesser than 0. So both are going to be negative. Now what will you do? You have ln and ln modulus of r is lesser than ln epsilon. So how will sign change? N will be, when this will go here, the sign with the equality sign, inequality sign will change, and you will get ln epsilon by ln modulus of r, because both are negative. Ln modulus of r is negative. So you choose your capital N to be ln epsilon divided by ln modulus of r and greatest integer function of this. No, there is a correction here. You have to actually there is a correction here. Please correct it. they are saying n has to be greater than 1 by epsilon. So 1 by epsilon is here, and your 1 by epsilon greatest integer will be here. We need all those natural numbers which are greater than 1 by epsilon. So basically you have to yeah, no, that's fine, because as soon as we have this only strict inequality, we are fine. No issues are there. Okay, so this is your capital N. If you want n to be greater than equal to some n, then you can choose your n tilde to be n plus 1. Everything will be fine. Let's move on to the next one. Question number 8. Prove that limit n tends to infinity 2 minus 1 by 2 raised to the power n is equal to 2.
Sir, is n in this case log epsilon by log 2?
Let's see. So 2 minus 1 by 2 raised to the power n minus 2 modulus is lesser than epsilon, then 2 get cancels. You get 1 by 2 raised to the power n is lesser than epsilon. From here,
In this we can return 2 raised to power minus n less than epsilon.
yeah, or 1 by epsilon is lesser than 2 raised to the power n. Now take the log. So ln 1 by epsilon is lesser than n ln 2. So n is greater than ln 1 by epsilon by ln 2.
Sir, but my answer is ln epsilon by ln 2.
Ln epsilon by ln 2.
I can done like that. 2 raised to power minus n is greater than epsilon. Then
Okay.
I take log.
So from here you directly did it, na?
Yes, sir.
So this will be minus ln 2 is
Yes,
lesser
sir.
than ln epsilon. Okay.
Then I can negative sign say I can multiply both sides of negative sign. Then the inequality is changed.
N is greater than minus of
ln
ln epsilon by ln 2, na?
Yes, sir.
So this is your answer, na?
Yes, sir.
So ln 1 by epsilon is nothing but ln 1
Okay.
minus
Okay,
ln
sir.
epsilon. So minus
Okay.
ln. Okay.
Okay, sir.
Or there is a one, you can also do it. We have 1 by 2 raised to the power n, na? Then this is lesser than 1 by n and lesser than n. So you can choose your n is greater than 1 by epsilon. So you can choose your capital N to be 1 by epsilon also. Okay. No issue.
Okay.
Because it's about tail. Okay. Next question. Prove that limit n tends to infinity 2 raised to the power 1 by n is equal to 1.
Sir, capital N will be equal to log 2 by epsilon.
Yeah, something like that. Let's see. So 2 raised to the power 1 by n is less, minus 1 modulus is lesser than epsilon.
Sir, in this we can write that also this na 2 raised to power 1 by n minus 1 is less than 2 raised to power 1 by n.
So 2 raised to the power 1 by n minus 1 is lesser than 2 raised to the power 1 by n.
Is less than epsilon. Then we take log on both sides.
Yeah. So 1 by n ln 2 is lesser than ln epsilon. Then n is greater than ln 2 by ln epsilon. Fine. Next question. Question number 10. Prove that limit n tends to infinity 3 raised to the power minus n is equal to 0.
In this case, n is equal to greatest integer ln 1 by epsilon by ln 3.
Yeah. So you will get n is to be ln 1 by epsilon by ln 3. Okay. Next question. Prove that limit n tends to infinity 10 raised to the power 6 into n by n square plus n is equal to 0.
Sir, in this n is equal to greatest integer 10 की raised to power 6 by epsilon.
Yeah, so 10 raised to the power 6 dot n by n square plus n is lesser than 10 raised to the power 6 into n by n square. Then this is same as 10 raised to the power 6 by n, which is lesser than epsilon. So your n has to be greater than capital N is equal to 10 raised to the power 6 by epsilon greatest integer. Okay. Remarks. It is very important to realize that the definition of the limit of a sequence is used to verify whether a proposed value L is a limit of particular sequence or not. So, but in most cases, we can make a guess about the limits by computing first few terms of the sequence. So what they're saying is, in the all the previous question, our limit was given. But if the limit is not given, we can actually make a guess about that. Second one. It is also important to realize that the convergence and divergence of a sequence are the property of the tails of the sequence. So the alteration of the finite number of terms of a sequence does not affect the convergence or divergence of the sequence. That is, you can see the example 1, 1 by 2, 1 by 3 up to 1 by 4, 1 by 5 and so on. This is the one sequence. Other one you choose to be, let's say 100, 10, 20, then again 1, 1 by 2, 1 by 3, then 1 by 4 and so on. The limit is still 0, right?
Yes, sir.
Yeah, so even if you change the finite number of terms, the limit which won't change. Here we change the first few terms. We can change any finite number of terms at any position. The limit still depends upon the tail of the sequence. Okay. Theorem. So if a sequence is convergent, then its limit is unique. Now, bounded sequence. So a sequence AN is said to be bounded if there exist two real numbers M and capital M such that M is lesser than An is lesser than capital M for all n belongs to natural numbers. So if a sequence is not bounded, then it is called as unbounded sequence. So let's see the examples. Muskan, can you tell me the example of bounded and unbounded sequence?
Sir, unbounded sequence are the natural numbers.
Yeah. And bounded?
Bounded
1
sequence
by n.
n by n, yes, sir.
So 0 is greater than lesser than 1 by n is lesser than equal to 1 for all n greater than equal to 1. Second one is natural numbers. It is unbounded. Third one is n square plus n. These are also unbounded. Okay. Now theorem. A convergent sequence is bounded. A convergent sequence is bounded. So let's see the proof. So let's suppose an converges to L. This means for all epsilon greater than 0, there exists capital N depending on the epsilon such that an minus epsilon modulus is lesser than N, is lesser than L, an minus L is lesser than epsilon. Okay, where L is the limit. So let an converges to L. This means that an belongs to L minus epsilon to L plus epsilon for all n greater than capital N. So now you consider your M to be maximum of L plus epsilon A1, A2 up to AN, because after AN plus 1, those are inside this interval. For that, we have chosen this max of this one. And M is lesser than infinity. So your AN is lesser than capital M, lesser than equal to capital M for all n greater than equal to 1, right?
Yes, sir.
So this sequence is bounded above. Now we need bounded below.
We take M is equal to minimum of A1, A2, L minus epsilon.
Yeah, you can take the minimum of these ones. So small m to be minimum of L minus epsilon to A1, A2 up to AN. Then your AN is greater than equal to small m is lesser than equal to capital M for all n greater than equal to 1. So which implies your sequence is bounded.
Sir, but converse is not true, na?
Huh?
Converse is not true.
Converse is need not to be true. I can give you the example. Consider this one. Converse need not to be true. Consider your AN to be minus 1 raised to the power n. This sequence is bounded. This sequence
Sir.
is like minus 1 plus 1 minus 1 plus 1. This sequence is bounded, right? AN is
Yes, sir.
between 2 and minus 2. So sequence is bounded. Or 1 you can also say. But the sequence is not convergent. Okay. Okay, then we will stop here.